Let's use the simplex method in algebraic form to maximize the profit of the company Optimal Humus. Recall the model in standard form for the humus problem. To transform this model to a system of equations, we first add the objective function as an extra equation where z represents the objective function value. Now the model is in simplex form. The three constraints we have now can be represented as a system of equations. To determine the initial solution, we highlight the basic variables in orange. Because z plays the role of basic variable in the objective function equation, it is also depicted in orange. In this system, we have only one basic variable in each equation, and each basic variable appears in only one of the equations with coefficient 1. Because the non-basic variables have value 0, we can immediately derive that S1 is equal to 240, S2 is equal to 480, and that the objective function z has value 0. This gives the initial basic feasible solution, the incumbent solution, with both x1 and x2 equal to 0, s1 equal to 240, s2 equal to 480, and z equal to 0. The next step is the optimality test. Looking at the incumbent solution and the objective function in terms of the non-basic variables given by the first equation of the system, we see that increasing either x1 or x2 from 0 to a positive value will increase our total profit z. This means that the incumbent solution is not yet optimal. Because the incumbent is not optimal, we have to select the non-basic variable with the highest rate of improvement. The two non-basic variables that we can choose from are x1 and x2. Looking at our objective function, we see that x2 has the highest rate of improvement. So, the entering basic variable is x2. We have to determine the maximum possible value for x2 such that the solution stays feasible. To determine this, we rewrite the system of equations using the fact that x1 stays non-basic, so equal to 0. This gives that z is equal to 7.5 times x2, s1 equal to 240 minus 4 times x2, and s2 equal to 480 minus 5 times x2. For the solution to stay feasible, x1 and s1 should stay non-negative. So we need to determine the maximum value of x2 such that both s1 and s2 stay non-negative. We can rewrite these two inequalities to x2 less than or equal to 240 divided by 4, which equals 60, and x2 less than or equal to 480 divided by 5, which equals 96. So for both s1 and s2 to stay non-negative, x2 can be at most 60. When x2 equals 60, s1 is 0, which means that s1 is a leaving basic variable. To determine the incumbent solution, we need our system of equations to reflect the change in basic variables from s1, s2 to x2, s2. Each of the basic variables should appear in only one constraint equation, and the coefficient of each term should be 1. We can do this by performing elementary algebraic operations. Multiplying or dividing an equation by a non-zero constant, adding or subtracting a multiple of one equation to or from another equation. We start with the current system where the new basic variables are colored orange. The only basic variable in the second equation is x2. We multiply this equation by 1/4 such that the coefficient of basic variable x2 becomes 1. Then we have a half times x1, 1 times x2, a fourth times s1, and a right-hand side of 60. Now we add the second equation 7.5 times to the first equation. So we have minus 1/4 x1, 1/7 as 1, and a right-hand side of 450. Finally, we subtract this second equation 5 times from the third equation. This gives 2.5 times x1 minus 1/4 s1, 1 times s2, and a right-hand side of 180. Now, because basic variables x2 and s2 each appear in one equation only, and the coefficients of their terms are 1, this makes it again very easy to read off the values for the incumbent solution. Because the non-basic variables x1 and s2 are now set to 0, we have x2 equal to 60, s2 equal to 180, and z equal to 450. To test if the incumbent solution is optimal, we look again at the objective function in terms of the non-basic variables given by the first equation of the system. This shows that we can still increase our total profit z by increasing x1 from 0 to a positive number, because x1 has a positive coefficient. So we are not done, but have to repeat the steps of the simplex method. In step A, we select the entering basic variable, which is the variable with the highest positive coefficient in the objective function. In step B, we determine the maximum possible value of the entering basic variable, such that all other variables remain non-negative. The basic variable for which its value is reduced to 0 because of increasing the value of the entering basic variable is the leaving basic variable. Then, in step C, we determine the incumbent solution by performing elementary algebraic operations on the system of equations. In the last step, step D, we check if all non-basic variables have a negative coefficient in the objective function given by the first equation of the system. If this is the case, we have reached an optimal solution.